Hi, welcome. Thank you for being here. Happy Tuesday. Um, so we have um, the project data source. It was technically due yesterday. At least, exactly two groups haven't given me it. So make sure you meet and talk about it and get it in by today. And there's, I believe, a progress report is due by this Friday as well. I would check on Canvas, but there's no internet. Um, but yeah, so the progress report is due on Friday, so make sure you're meeting and working on it to make progress. Today we're going to do minimum spanning trees and the traveling salesman problem, so it should be kind of fun. We're entering our kind of algorithms unit. If Canvas was up, I would show you that there's a new module for algorithms. I've named it, I think, chapter X or something, because we're kind of transcending the chapters. We're going to take elements from today we're doing the minimum connector, minimum spanning tree, and then we'll do shortest paths and so on. But we're going to kind of take a quick tour of algorithms. So if you're in 374 now, then there's a little bit of overlap because we're doing prims, Kruskalls, and Dijkstra's. But we'll also cover other things, like today we're looking at the traveling salesman problem, which is a new application of prims and Kruskalls that you probably haven't seen before, so hopefully it's helpful and useful. There's also an assignment on Canvas. It's like the MST TSP assignment. And we'll get to it at the end of the slide deck. I have the slightly less polished version of it in the slides. These slides, let me go up here. These slides are on Canvas. Sorry. But yeah, so we'll go through this. Probably it's just the whole slide deck today. The other thing is I'm currently not planning a packet for this unit. We'll see how that changes as we go forward. But there are still in-class activities, they're just embedded into the slides. So make sure you've got pencil and paper, and we'll go through these and you can just do that in your own notes. All right, hopefully, I don't know if it's going to record this part. I hope so. I think it will. I'm manifesting. Okay, so we're going to talk about minimum spanning trees. Last time we talked about trees in general. Now we're talking about, we also talked about spanning trees, but now we're talking about what minimum means. So one of the first incidences of looking for a minimum spanning tree happens in 1923 in a country called Moravia, which is modern-day Czech Republic, by a guy named, I'm almost certainly going to butcher his name, Otakar Borůvka. And he's a mathematician who was trying to find this optimal electrical grid network, right? So we're trying to connect different areas by electricity. And so the way that he phrased this problem is there are endpoints in the plane, in space, whose mutual distances are all different. We wish to join them by a net such that any 2 points are joined either directly or by means of some other points, and the length of the net is the shortest possible. So there's a little bit different language in here than we're used to. So there are endpoints in the plane. So this makes sense if we're talking about cities where there are two cities are a definite distance from each other. And there's this phrase that mutual distances are all different. And so that probably means that, so mutual distances, so the distance between any two cities are all different. That means that there are going to be unique edge lengths. So mutual distances are all different. He calls them a net instead of a graph or a tree. And so the way that we refer to this in our terminology is if we're given n towns in some rural area, what spanning tree, or maybe trees, has the least total edge length? So if we come up with a spanning tree, we want it to have the least total edge length. So the problem here is to find this minimum connector, the spanning tree with minimum cost. And so the cost is associated with the weight on the edge. So if this edge has weight 5 and this edge has weight 3, then we would prefer 3. And this is a kind of greedy algorithm. So the greedy algorithm is where when we're making a decision, we don't necessarily think ahead all that much. At any point, we just want to take the best possible option now. So we're kind of in like the 2-year-old thinking, where we're not necessarily thinking ahead of, oh, I don't want candy now because I'm about to have dinner and I'm going to be full from the candy. Like, you just want candy now. And so that's the idea here, where since we're looking for a minimum spanning tree, what ends up happening is we're going to take the least expensive option always. So not necessarily trying to plan ahead and say, oh, if we do this, then there's a lesser expensive option later, total. But no, at every step, we're choosing the least expensive option right now. So we're coming up with a minimum spanning tree, and that's the tree with the least total weight, and means that it's not possible that there's a smaller one. So the minimum possible. And we'll do this with weighted graphs. So the two that the book goes over are Kruskal's and Prim's algorithms. There are others. If you look at the Wikipedia page, there's Beruvka himself has an algorithm that doesn't get mentioned very often. I have it here in the slides for if we've got time today, we can take a look at it and try and pick it apart. There's also an algorithm called reverse delete, and then maybe a slightly better one that is not in the slides because I couldn't find easy pseudocode, Chazelle's algorithm, which also exists. So there's the main ones that you tend to hear about, and then others also exist. And this is typical for programming, where you tend to learn about the main ones, and then other people are working on the side to come up with new things. Okay, so we'll start with Kruskal's algorithm, where this is the version that they have in the textbook, where we start with this set of vertices, and each pair is joined by a weighted edge. So this is just saying we have a weighted graph. So our first step is to sort all the edge weights. So we list all the weights in ascending order, which means we start from the low numbers and go up to the high numbers. So we sort those first. And the step 2 is we draw the vertices and the edges. And so we choose, at every step, we choose the least weighted edge. Provided that when we do that, A, we don't form a cycle, and something that is omitted from this definition is B, that the new vertex is not currently connected. If you're in 374, we talked about this with the union find data structure, which is how we assure that this happens. So when we're adding, so this is the kind of building up method for the tree that we talked about last time, where we choose the least edge, and as long as that edge isn't going to make a cycle, and we're adding in a vertex that wasn't previously connected. And then you delete the weight from the list and move on to the next one. So then we repeat step 2 until all the vertices are connected, and then we're done. Maybe take a picture of this if the Wi-Fi is still not working, because we'll do this in a second. Cool. Are we good? All right, so in summary, we're choosing the edges of minimum weight where we don't create any cycles until we get a spanning tree. That's what we're doing. Okay, so we've got an example here. Let me make sure. So we look at this and we choose the least possible edge, or the least weighted edge, which in this case is AE, right? We've got a 2 and everything else is bigger than 2. So first we draw it A and E, that's weight 2. And then we have 2 options. So the next smallest is weight 4, which is either AC or CE. And at this point, I'm going to choose CE to break this tie, and in the next step, you'll do the other way. So if you break the tie the other way. So if we choose CE, and that's supposed to be a 4, then great. So C was not previously connected. Now it's connected. At this point, if we wanted to add in AC, that would make a cycle. So we can't. Okay, so we did AE, we did CE, we can't do AC. The next biggest one is, what, BC, 5? So BC, 5. So we did that. The next biggest one is either BE or AB. I don't think we can do either of those, because that would make a cycle, right? So no to that, no to that. And then the options are 7, 8, 8, or 9. And so we're going to choose the 7 and connect E to D. And then A, B, C, D, E. We've got all the vertices. So the graph is now connected, and we're done. And we have the minimum spanning tree. And so once we have the minimum spanning tree, great. Now we just need to say the weight is 2 plus 4, which is 6, plus 5 is 11, plus 7 is 18. So that's our minimum spanning tree with cross-goals. So now it's your turn. So do that process again, use cross-goals. I'm happy to go back if we need it. But at this point, I want you to choose AC to break that tie instead. Let me know if you want me to go back at all. All right, how's it going? Done? Cool. So our step 1 is still A need 2, but now we do AC, which is 4. And then what's the next step? Yeah. CB. Because now we've got 5. And that's the least. So we're done with that. And then, which, do we choose one of the 6s? Let's see, AB would make a cycle. EB would also make a cycle, so no. So then 7, ED. A, B, C, D, E. We've got our tree. Let's see the weight. So 2 plus 4 is 6, plus 5 is 11, plus 7 is 18, which is the same. So great. And so what does this tell us? We found 2 minimum spanning trees that have the same weight, but they're different. So this tells us that the minimum spanning tree is not necessarily unique, as in there's not necessarily just one of them, especially if you have repeated edges here like we do, then there's a sense that we could choose one and break the tie. But then the weight still has to be minimum. So 18 is still the minimum weight. Okay. So here's another example where we've got our distance table between some cities in Europe. And so we're going to run Kruskal's on this too. So so we look at this table, and first we choose the smallest edge, which is 3, right? So Paris to London. So we write that edge down. Paris to London, weight 3. And then we look around for the next smallest edge, which I think is Paris to Berlin, or London to Berlin. And so the tiebreaker that we're doing this time is, I think, London to Berlin. Yeah. Wait, I'm not entirely sure. Let me just make sure of that. Oh, London. Wait. Sorry, this table is also a little confusing. Okay, so London to Berlin or Berlin to Paris. And so I think we're doing London to Berlin. Okay. So we've got all that. And then we look for the next. So at this point, if we do, wait, no, I said London to Berlin, right? That's Paris. So we've got that, and so we could So we can't do Paris to Berlin now, because if we did that, then that would be a cycle. So we have to look at the next biggest, which I think is 8, which is Paris to Seville. So we've got Paris to Seville. So we've got Berlin, London, Paris, Seville. And so now the options are Rome or Moscow. And so I think Rome is the choice, since that's edge weight of 9. From Paris, so we've got Rome with edge weight of 9. And then we've got Moscow, and the smallest number here is 11 from Berlin. So then we've got 7 and 3 is 10. 10 plus 9 is 19. Plus 8 is 27. Plus 11 is 38 for a minimum spanning tree. Okay, so that's that one. Now we've got these distances for cities in, was it Ireland? Yeah, for cities in Ireland. So find the minimum spanning tree. How's it going? Are we done? Still working on it? All right, so what do we choose first? 56. And then what?
Athlon plus Liga, 71.
Okay. What's next?
Can we skip Limerick Galway?
Oh yeah, I think so. Because that's 64. So I think we do that first. Was it Limerick to Galway? Limerick, and that's 64. So Dublin or Wexford.
Athlon to Dublin, 78.
Cool. And then 96 Wexford. 96. That look right? Cool. The book does the math for me. This is 365. Anybody get anything different? Cool. All right, minimum spanning tree. All right, let's look at another algorithm, prims, which is, we have the same starting input, which is just our weighted graph. And so prims is a little bit different, where we start with any vertex. So instead of choosing the least weighted edge, we just choose a vertex and start there. And so this can be arbitrary. But what we do next is we we find the edge of least weight, joining a drawn vertex, that's a typo, should be 2, a vertex not currently drawn. Draw this weighted edge in the corresponding new vertex. So basically we're building up the tree still, where we have our tree in progress and there's multiple possible edges, and we choose the least weighted edges of all the possible ones, as long as it's not going to create a cycle. So we choose the least weighted edge, draw that, and repeat until it's all connected. You want to take a picture of this one too? If you want. Okay, moving on. So yeah, so first we choose an arbitrary vertex, and then we add on edges from the vertices that we already have. Joining a vertex that's already in T to a vertex not in T. So the same restriction applies, where as long as we'll add an edge, as long as it's adding something that's not in the tree. Okay, so we'll do this again. And the book has us start at Berlin. Yeah. Because the next one is, so A is tiebreaker and B is starting at Rome instead. So if we start at Berlin, then we choose the smallest option, so London or Paris, and in this case we choose London. So this is length 7, and so now we've got options from either Berlin or London. So we could do Berlin Paris or London Paris. London Paris wins because that's smaller. So London Paris 3 wins. Now we can go from Berlin, London, or Paris. So that's done. We can't go to Paris anymore. That's done. Berlin, that's done. So I think the option is 8 to go to Seville from Paris. So 8. And so now Seville is also an option, but I think we want to go to Rome from Paris. So we go to Rome for length 9. And now all that's left is Moscow. And so I think that's 11 from Berlin. That's 11. Which, to me, that looks like the same exact tree that we got before. Yeah, I think we just flipped it around. So it's just an algorithm to construct it in a different way. Okay, now your turn. So first off, if we start at Berlin and you choose Berlin Paris instead, what does that give you? And then what if you start at Rome instead of Berlin? How's it going? Are we done? Cool. I will note that this is just another way of representing a complete graph, where there's an edge between every city to every other city. Yeah. Okay, so if we choose Berlin, Paris first, where we start at Berlin and then we choose Paris, what's next? What edge do we add next? Yeah. Paris what?
London.
Paris, London, which is 3. That's 7. What's next? Yeah.
I got Paris to Seville.
Paris to Seville, which is 8. After that?
Paris to Rome.
Paris to Rome. Paris to Rome is 9. And then Moscow?
Berlin to Moscow.
Yeah. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I think we got all of them. What's the weight of this?
$38.
38, which is, I think, the same. Okay, what happens if we start at Rome instead? Yeah.
I'll go Rome to Paris.
Rome to Paris, which is 9. And then
Paris to Berlin.
Paris to Berlin. Paris to Berlin.
Paris to London.
Oh, London. And that's 3. And then
Paris to Seville.
which is 8. And then
London to Berlin.
London to Berlin. I think. Okay. And then Moscow?
From Berlin.
Yeah. I think that's the cheapest way to get to Moscow. Cool. Is it the same? Maybe not quite. Because in this case, we broke the tie by doing London to Berlin. But I think it gives us the same edge weight. So cool. Sounds good. All right. So there's an aside of how are we sure that this is the minimum spanning tree? That these algorithms actually definitely give us. The proof in the book is a little bit complicated, at least to me. So the way that it goes is we do this by contradiction, where we suppose that it's not. And so if we have some minimum spanning tree that we call T, so then we suppose T is not the minimum spanning tree. And so when that happens, then there's got to be another one. So there's got to be one that's actually minimum. Is a spanning tree that's minimum. So we'll call this other tree S. And then, let me pull this up just so I don't miss anything. So by doing this, there's going to be an edge in S that's an edge in S. Oh, no. So we have some edge E that's in our tree T that's smallest. So there's some smallest edge in T. So like for us, it would probably be Paris to London. That's edge 3. So there's some edge in T that is the smallest, but let's say that it's the smallest one that's not in S. So we've got these two trees. There's one smallest one that's in one, but not the other. If we add, so adding E to S would make a cycle, because that's how trees work. So would make a cycle. And so that means that there's some other edge in that cycle that is in S that's not in T. So if we had some edge E, there has to also be some edge we can call E prime that's, one of them's in T and the other is not in T in this cycle. So there's some edge E prime that is in S but not in T. So the next step in the book is, since this cycle must contain an edge E prime not contained in T, the subgraph obtained from S on replacing E prime by E is also a spanning tree. So if we take E prime, throw it away from S, replace it with the E, then we get a different spanning tree. So and then we get S prime, because it's not quite S anymore because we've taken an edge and thrown it away. Now we have S prime. And then, so the total weight of S prime does not exceed the total weight of S because we're working with the minimum edges here. And S prime has one more edge in common with T than with S. And so the idea here is we keep going and we keep choosing the minimum edge in T and replacing it. And so we do this process of where we reason that S and T have to be the same thing. And so if they're the same thing, then it's the minimum spanning tree. So then, so repeat, replace edges, so S ends up equaling T. And because of that, we supposed that T was not the minimum spanning tree. And so that is our contradiction. And so we get to the point where we say T has to be a minimum spanning tree. So that's kind of our reasoning for why indeed these algorithms give us the minimum. Okay. We ready for traveling salesman? All right. So, we talked about the traveling salesman a little bit at the very beginning of the class. This idea where if we have this map of cities and there's some roads between them, we want to be able to figure out how can we go all around the cities and return to our starting point with the minimum cost, right? So if we're on a school bus route, we want to maybe choose the least time total that it takes for us to get to all the bus stops and come back. It also applies to genome sequencing or like package delivery sequencing, where this is a problem like in the real world for delivery drivers, where they need to plan their route such that they can do this in the least amount of time and get back to home base. So it's a real world problem. However, and so we'll get to the however in a second. We can say this in graph theory terms, where we've talked about a Hamiltonian cycle, which is the cycle that goes all the way around the graph and returns to the starting point, hitting every vertex, right? That's the traveling salesman problem. In addition, we want to be able to find a minimum weight Hamiltonian cycle. So we don't want to find just any cycle. We want the one with the minimum weight. The problem about this is that this is really hard. So even if we say, oh, let's just brute force it and try and find like all the possible Hamiltonian cycles and then choose the best one, that one is n factorial, which is very not good. We could do a dynamic programming approach where we kind of write down answers as we go to try and calculate this. And that gives us n squared, which maybe isn't too bad, but then it gives us multiplied by 2 to the n, which is very bad. So that's also not good. And it turns out that the traveling salesman problem, is a very hard problem. It belongs to a class of problems called NP hard, which is there's problems that can be solved in polynomial time, so n to some power. And those are polynomial. Maybe the k is very high, but it ends up like it's still polynomial. But if it's non-polynomial, that's what NP stands for, and that just means it's really bad. And so there are these classes of really hard problems that we refer to as NP, NP hard, NP complete. And this is one of them. There's also, I don't know if we'll get to it in this class, but just to note that there's if you do some Googling, there's the millennial problem of does P equal NP, where can we find a way to change some very hard problem into something that we can solve in polynomial time? That's an open question. If you find the answer to this, you win $1 million and probably more. And then you either, if you find that it's not NP, P is not equal to NP, then we kind of go on with what we already know. If you found that P equals NP, then everything breaks. Because there's a lot of like cryptography and stuff that relies on the fact that P is probably not equal to NP. So yeah. So this problem is really hard, but we still want to be able to solve it. And so one of the things we can do is we can find, if we don't know exactly what the minimum cost would be, we could find an upper and lower bound for that cost, which is, we can get a heuristic, which is not necessarily the best, but maybe a good approximation of where we should go. And so we'll do this where the upper bound way to get there is kind of like prims, which is where we're going to build up a cycle and we're going to choose first we start with a vertex and its nearest neighbor, and then we put them into this cycle, and then we'll add the minimum weight edges as we go and add those into the cycle as well. So it's going to look kind of weird at first where we start with like a non-simple graph, but then as we go, we're going to add other vertices into this cycle and build it up that way until we have a Hamiltonian cycle that has some weight that is, hopefully, it's the upper bound of the minimum. So that's what we're going to do. And so this is the algorithm for that. So where we start with our weighted graph and we choose any vertex and find a vertex joined to it by minimum weight, that's where we do this thing. And then we draw these two and join them with two edges to form a cycle. And the book has us give the cycle a clockwise orientation. So like we get from city X to city Y in a kind of directed manner. And then step 2, which we repeat, we find a vertex that's not currently drawn and add the least weight. So this is kind of like, it's the prims approach where we choose out of the cities that we have, we choose the least edge and add that into the cycle. Sounds good? Do you want to take a picture of this one? Okay. So we've got this again. And here we arbitrarily choose Berlin again, just to make it easy. Let's actually put Berlin. We'll put Berlin over here. And so Berlin, London, or Berlin, Paris. We'll choose London to break that tie. And we set up this cycle. And so we say that there's some clockwise direction to this. So now maybe we can look at the minimum spanning tree that we got before, and we ask what's the shortest distance from either Berlin or from London. So I think that's London to Paris. So what do we want to do? Yeah, I want to put it over here. So we choose London to Paris. That's 3. Okay. London to Paris. And then after that, it is, like we've done this before, right? So it's Paris to Seville. And then once we've got Paris to Seville, so Berlin, London, Paris, Seville, and then I think the next option is Rome from Paris. So we put Rome in there. So because Rome comes from Paris, we put it next to Paris like that. And then, as before, we get Moscow from Berlin. So since we're coming from Berlin, we put it up here between Berlin, and London. And then we fill in the weights. So Moscow to Berlin is 11. Moscow to London is 18. That's an edge that we didn't have in our minimum spanning tree because it was a tree. London to Paris is 3. Paris to Rome is 9. Rome to Seville is 13. And Seville to Berlin is 15. Okay, and so this is our upper bound. And so if we add all these together, the book says this is 69. And so that's our upper bound. If you want to take this home to start at Rome instead of Berlin, we can do that. But I want to move on and cover the lower bound as well. So we construct this cycle, and at each step we ask, what's the shortest path forward that we can choose? And so we have this notion of we choose Paris from London, and so if we orient this clockwise, we say Paris comes from London. So we go from London to Paris, so we put it next to London in the cycle like that. And so we repeat that, inserting as necessary as we go around until all the cities are there, and then we add in the edge weights. So we said Seville best comes from Rome. Initially we said Seville best comes from Paris. So Seville from Paris was 8. And then we ended up inserting Rome in there. And so we kind of lose that edge, but we build up the cycle like that. And so this is our upper bound. So for the lower bound, it's slightly different. So the idea is we're going to have our graph and we choose arbitrarily a vertex and cut it. So we'll have this example where we've got this whole graph, and then we'll choose arbitrarily vertex A, the top one, and cut it out from the graph, and we'll look at the remaining graph. So the graph without that vertex and all its edges. In the graph remaining, we find the minimum spanning tree. So find a minimum spanning tree connecting the remaining vertices and calculate its total weight. And so first we cut it, then we find the minimum spanning tree of what's left. And then there's going to be vertices from that vertex that we cut. And what we'll do is we'll find the 2 smallest weights to add those to the cycle. And then because we need both of those weights in order to add it into the minimum spanning tree to get ourselves a cycle. And then add those 2 weights plus the weight of the spanning tree, and that's our lower bound. So we'll do this example with a different graph. And so here we choose to delete A. So once we delete A, we get the remaining graph, which is E, B, C, and D. And this is also a complete graph. So E to B is 6, B to C is 5, D to C is 9, D to E is 7, E to C is 4, B to D is also 4, and I think we've got that. So missing from this graph is A, and 2, 6, 8, and 4. Wait. B to D should be 8, right? Okay. Did I miss anything else? So E, D, C, and B. So this is missing from that graph. So now we just need to find the minimum spanning tree of this graph, which we can do with either algorithm. Maybe let's do Kruskal's. And so this gives us the smallest edge is EC, which is 4. And then the next smallest is BC, which is 5. And then ED, which is 9. And so the weight of this one is 4 plus 5 is 9, plus 9 is 18. And so now we've got this. And so now we look at the edges from A. And so we want to make a cycle here. And so since we've got this path, then it turns out that we want the, let me, ED, CE, BC. And so this says the two smallest edges that A has, which is AE and AB. That doesn't give us a cycle though, but so it doesn't give us a cycle, but it'll say what's the lower bound for it gives us a lower bound number for the weight. So if we add in, so 18, so if we add 2 and 4, then that gives us, no, that's not right. Did I make a mistake? I did. 7 plus 4 is 11, plus 5 is 16. 16 plus 2 is 18, plus 4 is 22. Okay, so this is our lower bound for the weight. And so what the book says is that we could get a better lower bound, because this doesn't actually give us a cycle. So we could choose a different one, choose a different vertex to remove. But for the purposes of the assignments, if you just show me this process and then give me the number, I'll be happy with that. So for the upper bound, I would like to see both the cycle and the number. For the lower bound, show your work as you go of give me the minimum spanning tree for the remaining graph and then choose the two smallest and then give me the number. So the actual solution to this problem is the cycle A, C, B, D, E, A, C, B, D, E, A, which has weight 26. And so if we look at the numbers that we had lower bound of 22 and upper bound of 69. And so 26 is most definitely in that range. Okay, so we're out of time, so we'll end here. I'll just note that if you want, you can look through those different algorithms. The homework is to find some data that needs the traveling salesman solution. First, find the minimum spanning tree using both algorithms. Tell me, what does that tell us about the graph? And then find the upper and lower bounds of this network for the traveling salesman problem. Show your work as you go and tell me what those numbers are. All right, thank you for coming. Hopefully, oh, the Wi-Fi's back. I'll see you on Thursday. All right, stop recording.